Do you want to know the number one reason why your CNC router has chatter? In this video, I will discuss the pros and cons of the two different Z-axis designs, either with moving rails or with moving blocks, and which influence this design has on chatter. I will also show the design and assembly of a very sturdy Z-axis, which is a proven concept on several of my builds, with a very clean look without visual cables, protected steppers, and integrated greasing solution. Hello and welcome to my channel. This is part 5 of my DIY CNC router build series. In the last video I finished a gantry and showed a greasing concept for machines with limited access from the sides. In case you haven't seen the first parts yet, I have linked the videos in the description below. Have you ever wondered why your end mill shrieks when you mill soft materials like wood? Well, there are many factors of influence like the chip load and the milling parameters, but the number one reason for chatter is the overall rigidity of your mill. When your machine is not stiff enough, you can play around with parameters and reduce chip load to cure it, but the underlying problem persists. And the key design element that determines the overall stiffness of your machine is the design of the Z-axis. There are two basic concepts, either with fixed linear blocks and moving rails, or with fixed rails and moving blocks. With my current design, I try to be as rigid as possible, and as I have discussed in the last video, the lateral stiffness of the gantry is a key element. To achieve that, I have tried to keep the distance between the gantry bottom and the fixture plate as small as possible, in this case 160 millimeters. This makes the gantry very rigid, but it requires a Z-axis design that makes the full gantry clearance usable work area, because 160 millimeter is not a lot of height. Here you can see a typical scenario of a 40 millimeter high part in a 4-inch vise and an end mill with a 40 millimeter stick out in a regular SK30 ER20 collar tool holder. The Z-axis here has fixed rails and moving blocks. The major benefit of such a design is that the spindle can move up high on the axis, well above the gantry bottom. Means that in Z0 safety height, there is no risk that the end mill can accidentally hit the workpiece. If we look now at the same gantry design, but with a Z-axis with fixed blocks and moving rails, you can see that the upper position of the Z-axis is reached when the lower end of the rails are flush with the lower blocks, which in turn are usually flush with the gantry bottom. But as you can see, the usable area under the end mill is in this case just 40 millimeter, so this is basically meaningless. You can cure this by moving the spindle up on the plate, but in case of an ATC setup, the plate could interfere with the magazine, and this also increases the risk of hitting work holding clamps. Alternatively, you can move up the position of the lower bearings. The most common argument from people who have chosen this design is the advantageous dissipation of forces by the close proximity of the linear blocks on the gantry and the Z-axis. But the higher the blocks go, the less this argument counts. So the usual fix of this problem is to increase the gantry height. However, this has a very negative effect on the rigidity of the whole machine. You can already see that this design cannot be as stiff as this design. And when we remember the formula for bending stiffness, the deflection under a given load is a function of the Young's modulus of the material, the cross-section, and the length. But the length goes in by the power of 3. So an increase of just 26% in length already doubles the deflection. In this case here, the gantry clearance, which is fairly similar to the unsupported length of the gantry side plates, would have to increase from 160 to 280 millimeters, and this would increase the deflection already by the factor of 5. And when you want to use a touch probe, you might have to increase the height even more. Here I touch off a part which is just 5 millimeters shorter than a gantry clearance without any issues. Now, coming back to the design with the moving blocks and the main argument of the other design, yes, in the fully up position, the flow of forces is not ideal. But first of all, this is a position where usually no milling takes place because it is the safety height. And secondly, it can be cured with a very robust and stiff design of the fixed plate that holds the rails. I will show later during the assembly how those plates interlock to reduce bending to an absolute minimum. On the other hand, when you mill flat stock directly on the fixture plate, the flow of forces is much better. In fact, it's even better than in the design with the moving rails. Because here the lever is quite long, because you have to lower the axis so much due to the increased height of the gantry. Another disadvantage of this design is that usually the stepper or servo is attached to the moving parts, means it not only has to lift the weight of the spindle, but as well its own weight. So all in all, for me and for this type of machine, a Z-axis with fixed rails and moving blocks is the better design. Let's have a look now at the assembly, but first a few impressions from the making of the parts. As you can see, again an interesting concept for greasing the linear blocks from the front due to the limited access of the grease nipples in the design and the enclosure. And these are the components that go into the Z-axis. From right to left, the linear components, timing belt, pulleys and taper bushings, tube and tube holders that I use as a drag chain substitute, the aluminum parts, servo with integrated brake, and the star of the show, the 4 kilowatt Spindle X30 ATC spindle with a 4-pole motor, 30k RPM and an SK30 interface. The first step of the assembly is to mount the linear rails. I start with them first because now it is much easier to align them. I use gauge blocks, parallels and woodworking clamps to pre-align the rails to the outer edge of the plate. This pre-alignment is then reconfirmed and adjusted with a dial indicator. Once the first rail is aligned and perfectly parallel with the plate, the second rail is adjusted in reference to the first rail. Next up is the assembly of the side plates, top and bottom plate. They form a very sturdy column, which is the fixed part of the Z-axis and is bolted to the cross plate of the gantry. The side plates have 3 mm deep slots and the other plates locate there with a very tight fit. With this type of design, the rigidity of the column is based not only on the strength of the force locking connection of the screws, but also on the form locking connection of the parts themselves. Once all the plates are in place, they are connected with lots of M6 bolts, which I torque up with 12 Nm, which is a hair above the recommended torque for the 8.8 bolts. I don't use higher grade bolts for this type of connection because the mating thread is in 5083 aluminum, which simply doesn't have the required tensile strength for the torque of 12.9 volts. After this, I could assemble the ball screw. I use a 60 mm TBI 04 screw with a 0 backlash double nut and 5 mm pitch on this axis. I first add the custom-made nut housing and then prepare the floating end with the bearing and the circlip. Then I mount the fixed bearing block. This is an FK12 block from SIG. These are really high quality blocks with angular contact bearings from NSK inside. Just the other day I saw a reel from a guy teaching on Insta how to fit these bearings, but in fact he taught everyone how not to do it. Folks, do not fine-tune the torque to rotate of these bearing blocks with the lock nut. The purpose of the lock nut is to lock, means secure the bearing block with the ball screw. Angular contact bearings can be oriented in two different ways, a so-called X orientation or a so-called O orientation. In X orientation, the inner rings have contact and the preload of the bearing pair is adjusted with the outer rings. In O orientation, it is the other way around. So when you tighten the lock nut and the friction and torque to rotate of the bearing block increases during this process, you have low quality bearing blocks, either with angular contact bearings in O orientation, which is wrong for this type of application, or worse, blocks with simple deep groove ball bearings, which cannot absorb axial loads and cause severe backlash in your axis. As you can see here, I apply as much torque to the lock nut as I can, using a wrench and a pair of pliers with smooth jaws in order not to mar the screw. But after this, it rotates as freely as it did before, which is a sign for an X orientation and a good quality bearing block. Good quality lock nuts have two inserts out of brass and the thread is cut through these inserts. So the grub screws do not push directly on the thread of the ball screw and cause damage, but they push the inserts on the screw and therefore secure the lock nut in place. And do not make the mistake to glue the grub screws in place. You will not be able to remove them in case you have to disassemble the ball screw. A tiny amount of medium strength Loctite is more than enough to secure them. The recommended torque to fix these grub screws is 2 Newton meter, but since my torque wrench starts only at 2.5, I do this by hand and feel. After the bolt screw is fixed, it was time to mount the spindle plate. Before that, I loosen again the bolts of the floating bearing block, because this will be adjusted later in the process. I set the correct spacing of the plate with a feeler gauge and bolt it to the linear blocks. Then I fix the bolt screw nut housing to the nut and the plate in the uppermost position, where I can still access the bolts with an Allen key. After this, I move the plate to the lower position and fix the floating bearing through 2 holes in the plate. This ensures the correct alignment of the bolt screw parallel to the linear rails. And finally, the bolts between the bolt screw nut and nut housing are secured and torqued one by one in order not to lose the alignment. After this, I remove the plate with the already mounted linear blocks again and take care of the grease concept. As you can see, there is no good access to the blocks because they are hidden by the side plates. And because of the limited access in the enclosure, I wanted to grease everything from the front. That's why I have drilled the 2 100mm deep holes in the top, what you have seen earlier. They end in the M5 thread of two push-in fittings, which are connected with 4mm pneumatic tube to the lower bearing blocks. The upper linear blocks are greased through the plate directly in the grease opening in the top. And finally, the plate is pushed back in place and the remaining bolts and fittings are added. And then it was time to mount the Z-axis to the gantry. I have two reamed 6mm holes in the design, one in the cross plate and one in the axis itself. A dowel pin acts as a pivot point, which makes the tramming of the axis much easier. Everything is loosely fitted because the final tramming will happen later on. First, I add the inductive homing switches and the motor with belt and pulleys. The servo has an integrated brake because servos run free when they have no power. So in the event of an e-stop or also after a regular shutdown of the system, the brake prevents that the Z-axis drops under its own weight. I add two small brackets next to the motor mount, which I use to adjust the timing belt tension. This is simply done with two M6 grub screws that push against the motor mount. The taper lock bushings are fixed with two grub screws to the pulleys. They need to be tightened step by step and finally locked with the correct torque, again step by step. And here you can see how I adjust the belt tension. Once this is properly set, the motor mount is bolted tight. An important step at this time was to confirm and adjust the tram of the axis. This is not the tram of the spindle, this will be done later. Here it is important that the axis moves up and down perfectly perpendicular to the X and the Y axis, so this has to be done in two directions. And I believe the final results are not too shabby for a DIY hobby woodworking router. The The business end of the axis is a 4 kW Spindle X3080C spindle. Spindle spindles come in a rectangular form factor and do not require an additional mounting bracket. They can be either mounted from the back into 4 M8 threads in their own housing, or from the front through 4 openings with a special rounded Allen key. For this mounting method, they come with a special fastener kit, which is basically a washer fixed with an O-ring to a bolt. And they have as well 2 reamed 6mm holes for dowel pins for additional shear strengths in the connection. However, I will use only one of them as a tramming pivot and secure the spindle additionally with the 2 lower M8 bolts from the back. And with this system, the mounting is actually quite easy. What helps is as well the fact that the spindle has an aluminum housing and weighs only 13 kg, so the whole process can be easily managed by one person. You just slide it over the bolt and washer combo and tighten the bolt in an iterative pattern, pushing the spindle as well over the dowel pin until it sits flush with the mounting plate. Last part to complete the axis is the tube, which acts as a drag chain and connects all the cables and air lines from the moving to the fixed part of the axis. This tube is from Egus and is designed for cable management on robots. The major difference to a regular drag chain is that it can be mounted in a 3-dimensional way. So I start in the middle of the axis, directly above the spindle, but end up on the far side of the column. The reason I prefer to do it this way is again the space restrictions that I have in the enclosure. The Gantry drag chain has a certain radius and it has to start in the middle of the axis, otherwise it would stick out of the side in the outermost position. But when the Z-axis chain ends in the middle and the Gantry chain starts in the middle, the cables and especially the water cooling and air tubes have basically no radius to go from one to the other. And with this design, this is in fact no problem. In addition, the bracket which holds the tube on the moving part has as well a fitting for greasing the board screw nut, which is completely blocked by other components. Servo and belt drive are then protected from dust with the backplate, and the cables are routed through the back in a special seal from Lab. And with this, the Z-axis and the mechanical part of my new DIY CNC router is finished. Let me know in the comments below what you think about this design and whether you like it or not. In the next video, I will route all the cables from the machine through the drag chains and move everything in its final location, which will be not so easy because the current weight is already well above 300 kg. If you liked the video, give it a thumbs up, subscribe to the channel and hit the notification bell. Stay tuned and see you next.